So on Wednesday, we started to know that how to address point, direction, and plans in this unit cell, right? So for the first one, for the point coordinate, we use QRS. You know, this point can be represented by these three numbers, for example. Okay, so this is the point coordinates. The second one is direction. This one is vector, or we call direction. So we need to follow 4 steps, remember? So the 4 steps, first one, this vector needs to pass through the origin, right? And then this vector need to do the projection to x-axis, y-axis, and z-axis. And then we got numbers, right? We got the length in the x-axis, y-axis, and z-axis. And then we need to make these 3 numbers to become a smallest integer. Okay, and then we use square bracket to blank to put these 3 numbers inside these 3 square brackets. For example, you can write 1, 2, 0. Okay, and this, why is this 0, 0, 0, 1? This square bracket. Why is this? This is, we have 4 coordinates, right? A1, A2, A3, and Z. Especially this is for what? This is for hexagonal structure, right? Okay, and then we know that we have families. We have members in the family, right? So for the direction, we use caret brackets. Caret brackets use this UVW, this caret bracket. So 100 caret bracket can be represent a family. And then you need to find out how many families. For example, it's 110, right? How many families, how many members in the family? There are 6, right? 1, 2, 3, 1, 2, 3, 4, 5, 6. There are 6 members in the family. Okay, so this is important, and vice versa. If I give you these numbers, can you draw the vectors directions here for me in a square, in a unit cell? This is the things you need to know. And also for the plan, this is a plan in the unit cell, and you need to follow 5 steps. The first step is origin. You shouldn't, this plan cannot pass through the origin. And then this plan has an intercept to the x-axis and y-axis and z-axis. So you have intercept. And then after that, you need to do the reciprocal of these numbers. Okay, reciprocal for these numbers. And then you do the reduction. Reduction means what? To make it become the smallest integer. And then you do the enclosure. Enclosure means what? You put the parentheses, or you put the 3 numbers in these parentheses. Okay? For example, parentheses 230, that will represent a plan in this unit cell. Okay? And also this 10001 parentheses, this is the hexagonal structure, right? You have 4 axes, A1, A2, A3, and then Z. 4 axes, and then you use these 4 numbers to represent the plan in the hexagonal unit cell. And we are going to talk about this today, very soon. So again, also we need to find members in the family of the plan. Okay, so we use brace brackets. Brace bracket, this one, brace bracket 1, 2, 3 means that there's a plan in this unit cell, and you have members in this family. Okay, so this is important So now let's finish the rest of the Miller index from Wednesday. The end of the Wednesday, we stop here. This is called hexagonal crystals. Of course, this is the unique cell for hexagonal crystals. So as you know, we have learned the directions in the hexagonal crystal, right? Hexagonal structure, unique cell. And this is the plan for a hexagonal structure, unique cell. So let's say that we know that's A1. Again, this is A1, A2, and A3, and Z axis, right? Okay. Okay, so now if we already learned this. This is the direction 1, 1, 2 over bar 0. Over bar means what? Negative, right? Positive sign and negative direction. Positive direction, negative direction. Okay. So this is the square bracket represent direction. Parentheses represent plans. Okay, you need to remember this parentheses square bracket. Okay. Direction. How about the plan? This is 1 over bar, parentheses 1 over bar 0, 1, 0. So this is the one represent the plan. How does it work? You see that? You do the 5 steps from the number 5 to number 1, right? So this you need to do what? You need to do reciprocal for this one, for 1 over bar. Reciprocal of -1, it will be also the -1. So A1 axis is here. So A1 axis minus A1 axis is here. And it reached the number 1, right? So it should be here. This one. So -1 will be represented here. And 0, reciprocal of 0 means what? Infinite. Infinite means what? You don't have intercept with the A2 axis. So it means what? It means this line means it's parallel to the A2 axis, parallel. Okay, this is the one. And 1, reciprocal of 1 is 1, right? So A3, 1 is here. So you point here. So you already have a line. And how about 0? 0, reciprocal of 0 is infinite. Infinite means that the plane is parallel to the axis. So it should be this one. So as a result, you know this plane represents this Miller index. Okay. Okay, let's take a look at another case. This one. Again, reciprocal 1, that will be 1, right? That will be 1. Reciprocal 0, that will be infinite. Infinite here. You have a line here. Reciprocal of -1, 1, -1 here. Reciprocal 1, that will be 1, right? So intercept in z-axis is 1, so it's here. So you know that this is the plane represent the Miller index of the parenthesis 1, 0, 1 over bar 1. Okay? Right, so this is 0, 0, 0, 1. This is the plane. Okay? So this is the one I just showed you. So please remember this. Do the practice. Okay, so there's the 4 index scheme and the 3 index scheme can be converted to each other. As I just told you, the case of the direction. The plan also apply to the same concept or same scheme. So, but this is easier. So I is determined by the sum of the h and k. So h and k, this I in this middle index for the 4 directions, this I, you have an extra I here. So I will be the minus bracket H plus K, this one. So this is very easy. So you don't need to worry too much about this. Okay, so this is a summary. We just talked about this with you. So please remember, he's a great guy. We use his name to represent the middle index. Okay, so now let's move to another topic, which is atomic arrangements and the interplanar spacing. Atomic arrangement and interplanar spacing. So now let's take a look of the FCC 110. This is represent direction or plan. Which one? Parenthesis 110 is the plan, represent a direction or a plan. A plan, right? A plan. Okay, good. Be careful about this. Okay, be careful about this. No, I just give you a hint. Okay, and so this is the 110 plan. As you know, this x-axis, y-axis, and z-axis. So it's 110, right? 110 means what? You reciprocal of this is infinite. So this is the plan. And you know, we name this atom as A, B, C, D, E, F. So as you see, this is A, B, C, D, E is this one, F. Okay. And then if we take a look of in two-dimensional, this three-dimensional view, right? This is the two-dimensional view. If we have a top view of this 6 atoms, it looks like this. There's no touch between each other. As you can see, this one and this one, there's no touch. Why? Because you have a one atom in the face, right? This is in the corner. This is in the face. So there's no touch between the A sphere, A atom and B and D atom. So it looks like this. So what we call this is a two-dimensional repeat unit. This is also a repeat unit, the smallest. Not this one. This is repeat unit, and you repeat like this. Repeat like this. Okay? Two-dimensional repeat unit. So when you see the plan, it looks like this. 1, 2, 3, 4, A, B, C, D, E, F. How about BCC? You know, this is 110, right? FCC 110. This is BCC 110. What is this? It looks like this. And when you take a look of this unit cell in two-dimensional view, and you will see this A prime, B prime, C prime, D prime, E prime. So as you can see, this C atom touch A, B, E, and D prime. No problem. Easy. So this is repeat unit. So when you take a look of this one FCC 110 and BCC 110, you find something different, of course, because their unique structure is different, right? Okay, and how about BCC 100, 110, and 111? So 110, this is 110, right? This plan. Two-dimensional look like this. 110, 110, this one. Looks like this. And 111 is this one. So just give you a quick quick information about how do you see from this unit cell to become two-dimensional. As you can see it here, this one. And you only have this part and this part. There's nothing in the middle. Why? You might say, well, Professor, why you didn't include this sphere here? Why? Because the center of this sphere doesn't in this plane, so we don't count this plane. Okay. So important thing is, the center of this sphere is not in this plane, so we don't draw a sphere here. Only in the sphere which has touched the plane, the center of the sphere touch the plane, inside the plane, then we draw the sphere. For example, this one, right? This one is here, the center. This is the center. So you draw these spheres. In the case of this one, right? The center. Of course, this is in the center. Okay, this is important to know. So the parenthesis 111 plane does not pass through the core, which is the center, right? Of the center atoms. That's why you don't draw a sphere here. No problem. So now, next one is interplanar spacing. What's interplanar spacing? The definition of interplanar spacing is that the distance between the adjacent planes of the same Miller indexes. For example, if you have 1, 1, 0, 1, sorry, 0, 1, 0, 0, 1, 0 is this one. So what's the interplanar spacing? Interplanar spacing means that the distance between two planes, and this plane equal. These planes talk about the same plane. For example, this one. I hope you remember. You just move the origin from here to here. This also represents 0, 1, 0. Okay, it might be 0 minus 1, 0, 1 over bar 0. But it's the family. They are the family, right? The member of the family. So we are talking about the same thing. So this is what we call interplanar spacing. Interplanar spacing. This is the easy way, but I want to give you a formula equation. Ladies and gentlemen, please remember this equation. I don't give this to you in your final exam. So you need to remember. So DHKL equal to A divided by what? Root H power 2, K power 2, L power 2. K represent this one number. H represent this number, the first number. K represent the second number. L represent the third number. Okay? For example, in this case, this is the plane 0, 1, 0. So the D is the interplanar spacing, right? D, HKL. So D 0, 1, 0 equal to what? This is 0, here is 0. 1, here is 1. 0, here is 0. So root 1 power 2, that will be 1. So as you know that D0, the D spacing of 0, 1, 0 plane is equal to A. A is what? Edge length. Edge length. Okay? And you can see very clear. But if I give you a little bit complicated number of the Miller index, that will make it more complicated for you to draw and to find out. So you use this equation to find out the interplanar spacing. Okay, I give you an example of D111. So D111 is this one. This one is also 111. This is the 111. Because what? Because they are the member of the family. The same thing. So you want to talk about the distance between this plane and this plane. This is what we call D111, interplanar spacing. So if you put these numbers in this equation, then it will be easy for you to know. That will be what? 111. That will be the D111 will be equal to what? A divided by what? Root 3. Right? Root 3. That's the answer I want in your final exam. Okay, so I give you some examples. For example, this 0, 0, 1, 1. This, we just talk about this, right? 0, 1, 1. How about 0, 2, 0, 2, 0? 0, 2, 0 looks like this. Because if you do the reciprocal of the 2, that will be half. That will be half. Okay, and it looks like this. So as you know, the D spacing is easy. A divided by 2, half of A. This one is half of A, and this is A. So as we can see, every parenthesis 1, 0, 1, 0 plane is a 0, 2, 0. This one can show that they are the same plane, right? Okay, but every 0, 2, 0 plane isn't a 0, 1, 0 plane. This one doesn't belong to this one, right? Not everyone. Every planes belong to this one. Okay, this one, all the planes all belong to this, but this one doesn't belong to this. Easy. Okay, here I give you an example of 1, 1, 1. Please do this by yourself. I just told you, right? A D 1, 1, 1 is A divided by root 3. Easy. I hope all the things I want you to know is this one, this equation. Please remember. Easy. So as you know, if the numbers increase, the D spacing decreased. Okay, this is the things you need to say. Okay, this is the example for you to know. Okay, so are you okay? Are you okay with this information? Good. So let's move to the section 3.11, linear and the planar density. You know, when we talk about density, we always talk about density. The definition of density is what? Definition of density is weight divided by volume, right? And this is what you need to learn, or you need to remember. This is what we call theoretical density. Okay, so you might regard this as a volume density because we are talking about volume in the button here. How about linear density? How about planar density? Linear density means what? This is what we call linear density. How many atoms pass through this vector or pass through this direction? Then what we call linear density. How about planar density? Planar density means how many atoms in this plane. You might regard how many atoms in this unique cell, right? That's by volume. By the plane, by the area is how many atoms in this plane. This is what we call planar density. Okay. You might think, well, Professor, why should I learn this? We will find out very soon. Okay, so let's have a look over the linear density. The definition of linear density is what? It's we use LD for short, okay? So the numbers of the atoms centered, remember, this is the key word, centered. The number of the atoms centered on direction vector. This is called direction vector, right? We call direction. Okay, divided by what? Length of the direction vector. So this length is that. This is the length. So what's the unit of this density? Linear density. What's the unit? What's the dimension? I should say. What's the dimension? On the top is number, right? So it's nothing. By what? By the length. By the length. This is the dimension. Okay, the unit of the linear density is, you can write nanometer minus power minus 1. Okay, let's have an example of this. An example of linear density. Okay, if you want to write a linear density of the square bracket 110 direction for the FCC crystal structure. This is FCC, right? FCC is 545. 5, 4, 5. Okay, there are 6 atoms in the 6 phases. There are 8 atoms in the 8 corners. Okay, so this is the direction of 1, 1, 1. So let's try to find out what's the this, and you have X atom, Y atom, Z atom. Okay, 3 atoms, and this is the direction 1, 1, square bracket 1, 1, 0. Okay, let's take a look of the 2-dimensional view of this unit cell. This is one X, Y, Z. This is reduced field model, right? This is half sphere model. As you know, half sphere model, the atoms touch to each other in this plane, in the bottom phase plane. Bottom phase plane tell you that X, Y, Z here. And of course, we understand this is the R, radius of the atom. Okay, so let's write down what's the definition of the linear density 110 is number of atoms centered on the direction divided by length of the direction vector. So what's the number of the atoms centered on the direction vector? How many? How many atoms? Have a guess. How many atoms? You might say, well, Professor, 3. 3, right? 1, 2, 3. But you don't count this as a 1. You only count half because this atom need to share with this unit cell here, right? So you only have half of this, 1 of this, half of this. So that will be 1 plus half and then half. The answer is 2. So no problem, right? Because you understand the reason we use only half of this atom is this part share with another unit cell or repeat unit, right? Okay, so this is 2. How about the length or the length of the direction vector? How? There are 4R, right? 4R. Share atoms with one another adjacent unit. Okay, so this is 4R here. So this is the answer. So in your final exam, if I tell you the radius of copper, or the radius of silver, or the radius of gold, I give you the number here, so you can put a number here, so you can tell me the correct answer of these questions, right? How about planar density? We use PD. So I'm sure you know that if we use PD, if we want to know that the planar density of this plane, and the definition will be the numbers of the atoms centered on a plane divided by area of the plane. So easy. So the unit is also this is the nanometer power -2. Okay, let's take a look of this plane. We talk about the same thing, right? This plane, and this plane, the members of the same family, right? This 1, 2, 3, A, B, C, D, E, F is all equal to this one. So the parenthesis 110, parenthesis Miller index in the face center cubic unit cell is this. So this is 2-dimensional structure. So two-dimensional structure A, B, C, D, E, F. Right. So how many of these in this plane? How many areas of this atom in this plane? Quarter, right? Quarter. How many of these? There are 4 quarters, right? This one is quarter. There are 4 quarters. There are 2 half of the atoms. Okay, so can you tell me the answer of the number of the atoms centered on a plane? How many of them? Anybody home? Hello, anybody home? I will knock your atama, your head. Anybody home? Wake up in the morning. Okay. Anybody home? Piece of cake, right? Okay. 2. So area of the plan. Tell me area of the plan. R, 2R, right? So this is 4R. How about this one? Hope you still remember, you need to find the relationship between A and R. Right? This is A, right? This is A. And if you know the relationship between A and R, you just do this. Okay? So if I tell you the radius of the copper in this case, or radius of the iron in this case, and you just put the length, the radius in this symbol here, and then you got an answer. Okay? In your final exam, please, this is important. Okay, so as you know, you might ask, Professor, why we need to learn this? That's because we want to examine atomic packing of the crystallographic plane. You know, we want to know how many, what's the plane which has the most atoms on the plane. Why we need to know this? Because if you regard atom as a catalyst, as a reaction site, if you have more atoms in that plane, that means you have more reactive site. That means the reactivity will be high, right? Okay, so this is, or if you regard the atom as a catalyst, and if you have more catalysts on that plane, that means what? That means kinetic speed, the kinetic will be very high, very fast, because you have more atoms on that side. So the iron foil can be used as a catalyst. The atomic packing of the exposed plane is important. You have more, then you have more reaction, quicker reaction. Okay, you have less, you have the speed of the reaction is not that high. Okay, so the question here is, I want you to, sorry. So I just told you this, right? So the question is, if I want you to draw, this is FCC. Sorry, this is BCC, body center, right? 414. Okay, I want you to draw a plane which is 100. 100 is this one, right? And 111. 111 is this one. And I want to ask you, I want you to calculate the planar density. The planar density, if you have a high planar density, means what? You have more atoms in that plane, right? Okay, I want you to calculate the planar density of this and this 110 and 111. And at that time, you will know which plane has more atoms. In that case, you have more atoms. Reaction, if you put that reaction, if you put a plane on the surface of the iron, of the copper, then you have faster reaction. Okay? So calculate the planar density for each of these planes. This is important. And now this part is very important. I want you to remember because this is very practical. I want you to realize the density of the planar density of 100 parentheses and also the parentheses of the 111. I want you to calculate the planar density of each of these planes. So let's firstly take a look of the planar density of 11100. So 100 iron. So 100 iron is the BCC structure at temperature below 912 Celsius. So you understand this is BCC structure. BCC structure looks like this. So what's the 11100 plan? 100 plan is this one, right? This one. So it looks like this. And you understand the planar density. The definition of planar density looks like this. So 100 in 2 dimensions, it looks like this. So this is the plane of the 100. And you understand this is the atoms on the surface only. This is not atoms on the surface. Okay, this one. So it looks like this. And then you need to find out repeat unit, of course. In order to do the calculation of this, you need to find out repeat unit, right? This is repeat unit. Okay, and then tell me how many atoms in this. You know the numbers, right? How many atoms? So this is 8 equal to this. Of course, you understand how to do the calculation now. It should be 4 divided by root 3, right? Okay, so as a result, it looks like this. And if I told you the radius of the iron at room temperature is about 0.1241 nanometer, and then you need to do you need to do this. This is the I will tell you some information like this is iron, this is the BCC structure, and the radius. These 3 information I will give you, and you need to take care of the rest of them and give me the answer in your final exam if this question show up in your final exam. I haven't made my decision yet, but this question might be possibly in your midterm in your final exam. Okay. So planar density is what? Is how many atoms in this plane? 1, right? 1. Okay. It's atoms per 2-dimensional repeat unit. So in the bottom, that means if you A power 2, right? This is the area A power 2. A times A. So equal to what? It's areas per 2-dimensional repeat unit. And now you know the relationship between the edge length and the radius. So you put this number in. Okay, you put this number. And of course, I told you that radius of the iron is 0.1241. So you put this number in here. Bring your calculator when you come to your final exam. So the answer is 12.1 atoms per nanometer square. So what does that mean? There are 12.1 atoms per 1 unit, 1 repeat unit. Right? Sorry, it shouldn't be like that. There are 12.1 atoms per 1 nanometer square. So you know the density, you know the planar density now. Of course, if you want to change it to SI system, you make a millimeter. You meet a meter square, and that's the answer. That will be 1.2 times 10 to 19 atoms per meter square. Okay. Next, 111 iron. This is 111 ion, right? This is 111 ion. This phase, and then this is the one. And if you still remember the the center of this, the center in this center atom doesn't touch this plane, so we don't count the atom in the center here in this two-dimensional repeat unit. So it looks like this. So the question I want to ask you is this high planar density or of the 111 or 100? Which one is higher in terms of the planar density? So let's take a look at three-dimensional view of this. This is a little bit, use your imagination. This is a little bit complicated. Okay, I want you to remember this. If you take a look of this, this is the plane of the 111, plane of 111, plane of 111. So if you think of this, you know, the dash blue line here. This one represent this sphere. Okay, this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Sorry, am I wrong? No, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and the pink ball represent the atoms above the plane. So actually, this ball is above, right? Above the plane, the blue represent this blue one. This ball represent the same thing here. So the atoms above the plane, this one above, and this one below the plane, below. So when you think of this, you need to find the repeat unit. You know the triangle that cannot represent the repeat unit. Triangle cannot, right? Okay, so you need to find repeat unit from this plane. So can you tell me the repeat unit? Can you? Repeat unit is this one. This is repeat unit. Repeat unit. Okay? Use your imagination a little bit. But anyway, when you see this equation, when you see this question in your final exam, you don't need to draw this, but you need to realize this is the repeat unit. You need to remember this is the repeat unit. Okay, so and now we need to find out how it's one atoms in a plane per repeat unit, right? It's one atom. How many atoms in this repeat unit? This one doesn't count. This one doesn't count. But only this part, and this part count. So there's only one atoms in a plane per unit surface cell or repeat unit. This one. You know, this area count only one. And of course, you understand this distance is what? Root 2a. Root 2a. Okay? Remember this? And this is, of course, this is height. H, you know that the root 3 per 2a. This is easy. Okay? So the most difficult part is this repeat unit. So try to remember this. So the area of the two repeat unit is equal to what? This is equal to, if you know the length of this, if you know the height of this, of course you understand this is the end. This is how you calculate, right? This times this. And then you do the simple calculation. You understand this is the root 3a power 2. An important thing is for the BCC, you need to know the relationship between a and the radius again. So you know this a equal to this, as we just mentioned in the previous slide, right? Okay, because I won't tell you the age length in your final exam, but I will tell you the radius of the atoms in your exam paper. So please remember the relationship between A and R for BCC and FCC and the SC. SC stands for simple cubic structure, right? Okay, so do simple calculation. So the planar density is what? How many atoms? I just told you there's one, right? There's one. So, and then you need to know the repeat area of the repeat unit. This is area of the repeat unit. And then R is what? R, the radius of R is 0.1241, as I just showed you in the previous slide. And you do the calculation of this, you got to answer 7.0 atoms per nanometer square. But if you want to use in SI unit system, then now be 0.7 times 10 to 19 atoms per meter square. So if we compare to this one, the density of 100 and 111 here, this is 100 and 111 here. And then we know the planar density of the 100 is 1.2 times 10 to 19 atoms per meter square. And the 111 is 0.7 times 10 to 19 atoms per meter square. So which one has a higher planar density? Which one? 100, right? 100 of iron. So once you have a brick, for example, a brick, or if you have a sheet, if you have a sheet of iron, and then you want to have more atoms of the iron on the surface, now which plan if you have two choices, 100 or 111, which one you want to make it on the surface in order to have high reactivity or faster reaction? Which one? Which plan you want to make it on the surface? Plan 100, right? Plan 100. Okay? So when you design the material, when you design some reactors, you need to do this. You need to know the material science before you do the reaction, before you become an engineer to design the reactor. Okay? So this is another example of the silicon orientation. So this silicon orientation tells you that this is the plan of 100, this is the plan of 110, this is the plan of 111. Okay? So if we have a gun, if we have a bullet, you want to shoot this silicon wafer or silicon crystal, and you want the bullet to stop in the middle of this silicon, which surface you want to choose in order to let the bullet stuck in the middle rather than just pass through? I shouldn't say bullet, I should say you have another atoms. For example, like boron or arsenate. You want to shoot the boron or arsenate into this crystal. And you want the boron atom to trap in the crystal, in this silicon crystal, not instead of let it pass through. Which one you want to choose? It looks like 111, right? Because what? Because the atoms might easy to pass through this. And this might be the answer. just for the information. So you have different planar densities with 1, 0, 0, 1, 1, 1, 1, 0, and 1, 1, 1. Okay. So why linear and planar density? Linear density and planar density are important considered relatively to the process of sleep. So when we talk about a chemical process, we know that we just give you an example of the catalyst or reactivity, right? But on the other hand, in terms of not chemical, in terms of mechanical, and mechanical guy and mechanical engineers, they need to think of sleep. Sleep means that you have two phases, and this phase might slip to another place. So this is called sleep. So they need to think of the linear density and the planar density. Okay, so sleep is that the mechanism by which metals plastically deform. So we will talk about this in the section in the chapter 4, I think. So sleep occurred on the most dense packed closed graphics planes. In those planes, along the direction has the greatest atomic packing. So what does that mean? If you have for example, if you have a greatest atomic packing on this surface, so between these planes, these are the highest close pack. So this plane is easy to slip, and this is called what we call what planar density. Sorry, in the planar spacing, right? In the planar spacing. So this is called slip. Okay. Right. Let's go to the end of this. It's called 3.12 close pack crystal structure. What's close pack? Close pack, as we just mentioned, the slip, right? If you have close pack crystal structure, and between the parallel plane is also the close pack, and this is easy to do the slipping. Okay, so close pack plane of atoms is the most efficient packing of the equal size spheres or atoms. The both face-centered cubic and hexagonal close pack crystal structures. Okay. So FCC and HCP, they have 74% of the space occupied by atoms in a unit cell. I hope you still remember, as I just told you, FCC and HCP, their packing looks the same, only different packing sequences. Here, I just want to show you here. So you have 8 atoms. Well, you have 8 layers, and you fill up all the atoms. This is close packed. You cannot put more atoms in this layer anymore. So this is close packed plan. Okay, and then after that, you want to put the layer 2. You have 2 choices. One is B sites. One is B sites. One is C sites. Can you put into the A site in the layer 2? No, you cannot, because there's no place. You cannot, right? Can you imagine that? Can you? No problem, right? Okay, so you have 2 choices in the layer 2. One is B site, one is C site. In this case, we put in the B site. Of course, you can put in the C site if you want to. So when you put in the B site, and then next, you have 2 choices again. Put in the C site or put in the A site for the layer 3. Okay, so if you put put the atoms in the C site, that will be called ABC packing sequences. And this crystal structure we call FCC crystal structure. And this surface is as 111 plan. So we say ABCAPC. But if you put the atoms in the A site in the 3rd layer, that will be called AB packing sequences or stacking sequences. And this is what we call the hexagonal closed pack, and the surface, the plane is 0001. It can be AC or it can be AB. So this is called stacking sequences, and also this is the closed pack structure. Okay, this cartoon show you that the packing on the left hand side is FCC, on the right hand side is HCP. Okay, there's three. As you can see, they show the difference. Right, I think we run out of our time. Please read this by yourself and start. Right, so that's it. Today, any questions? Now, if you do have, please come to me after the class.